The planets have fascinated us for millennia. We've sent dozens of spacecraft to explore them.
Touchdown confirmed. Proceed.
And now, our exploration of the planets is even taking us out beyond our own solar system.
Liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
We've made discoveries we never imagined.
I have no idea how those mountains could be formed.
Fantastic to really capture how close Mars was to Earth in many of its features.
I think my jaw hit the floor. I'm pretty convinced it's really out there.
The Sky at Night has covered every major space science discovery in more than 60 years of occasionally quirky broadcasting.
Line your finger up with my nose. It's absolutely tremendous. I'm going to do just a little mathematics. Please don't be frightened.
We're going to use this archive to travel on an epic voyage of discovery.
Good evening. Good evening. Welcome.
Welcome to the Sky at Night's Guide to the Planets. For thousands of years, our only view of the planets was from here on Earth. But since the start of the space age, we've sent over 60 probes to visit them. These probes have led to a transformation in our understanding. When I was growing up, there were 9 of them, each with its own unique orbit around the Sun and its own unique characteristics, unchanged since their formation. It was even thought possible that our solar system might be the only one in the galaxy, the only star with planets in orbit around it. How wrong we were about almost everything. You get some idea of just how far we've come by looking at the 2 planets closest to Earth, the rocky worlds of Venus and Mars. If there's one planet in the solar system that's fascinated us more than any other, it's Mars. Through the years, the Sky at Night has returned to look at Mars over and over again. No other planet has been studied more, and no other planet has revealed such an extraordinary story of transformation.
Altair and the Eagle, you can find Mars quite easily. In the Scorpion...
As recently as the 1960s, we thought it might be a living world, with plants on its surface. But then, in 1969, came Mariner 6, and that changed everything.
And Mariner 6 came down over this direction, over these so-called deserts. Well, the question is, of course, are these dark areas due to organic matter, vegetation if you like, or are they not?
The answer became clear as soon as Mariner 6 sent back close-up photos. Nothing but bone-dry desert and craters.
Now, what about this all-important question of life on Mars? Do you think that these dark areas are due to anything organic? What do you think about it?
Primitive life there may be. I don't even think so. Intelligent life, certainly not.
So, in other words, you rather think that Mars is a dead planet?
Absolutely dead as a dodo.
Mars was brutally cold, with virtually no atmosphere. Vegetation didn't stand a chance, as the Sky at Night demonstrated.
Just to show you the fate of higher plants, I brought along tonight 2 cacti. This cactus has been quite healthily growing under Earth conditions, and you see it's quite a nice, firm-looking sort of cactus. This one here has spent one night under Martian conditions, and I think you can see without any doubt that it's got a distinctly morning-after appearance.
Mariner 6 changed our approach to the Red Planet. There was no complex life now. That was certain. But had it always been such a harsh environment? Our focus shifted to the past, and one big question: had there ever been liquid water on Mars? In 1976, the Viking orbiter took a series of stunning images that hinted that the surface of Mars may have once been flowing with water. We looked back at Viking's striking achievements in 2017.
So this is from one of the Viking orbiters, and it's not a single picture. It's lots and lots of pictures. It's a mosaic that's been put together.
But it's glorious.
It's absolutely fantastic. Just looking at these pictures started to really capture how close Mars was to Earth in many of its features. It's got these volcanoes, which are like the volcanoes on Hawaii. It's got this rift valley, which is like East Africa. And, of course, it's got its ice caps. But you've also got the features that on Earth we would interpret as being from rivers. So you've got something that looks as if it's going out into a huge delta. You've got other channels, meandering channels.
The photographs taken by Viking indicated that in the past, huge bodies of liquid water may have shaped the landscape. But with only aerial images to go on, this could only be a theory. To get proof, we needed to land on the surface of Mars. Easier said than done. The problem is that Mars has an atmospheric pressure just 1% of that on Earth. That makes it hard to use the atmosphere to slow a spacecraft down, enough to make a soft landing. 19 spacecraft have been sent to land on Mars. Only 7 have successfully managed it. The latest, NASA's Curiosity rover, was the biggest and most ambitious.
We have ignition and liftoff of a Delta II rocket carrying NASA on an odyssey back to Mars.
It arrived in 2012, and the Sky at Night reported on the complicated procedure used to deliver the rover to the surface.
Pete, can you start talking us through what had to happen to get it safely onto the ground?
Yeah, sure. There are a number of things that had to happen. The first is to enter the atmosphere at the right point so that the heat shield could slow the craft down enough to slow it down from 13,000 miles an hour down to, about 1,000 miles an hour by the time the atmosphere had done its job, and at which point the parachute could then come out for the first time.
Parachute deployed. We are decelerating. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending.
We even got a photo of Curiosity on its parachute.
From the Mars Reconnaissance Orbiter. And it's great to be able to see this, to have a spacecraft taking a picture of another spacecraft descending, but that wasn't the hard bit. What happened next?
Curiosity dropped down away from its back shell and parachute.
We are in powered flight.
And then moved away from the parachute and left it behind, and then started to descend on its own powered rockets then. So coming down, kind of 8 thrusters controlled it, slowed it down, make sure it was all smooth. It slows down to an almost kind of stop, hovering above the surface.
Sky crane has started.
So about 20 meters above the surface, then Curiosity, the rover part, then descended on its own kind of cables on this sky crane technology. This was the part that we'd never seen anything like this before.
UAV stable. UHF is good. Touchdown confirmed. We're safe on Mars.
Like other rovers before it, Curiosity was looking for clues into the past. But how could we piece together the story of what happened with photographs of Martian rocks? The answer was to apply skills we've perfected here on Earth, as geologist Ian Stewart explained.
This rock face is part of the Jurassic coastline in Devon. It was formed around 240 million years ago, and it provides a detailed record of different environmental conditions.
There's a whole set of layers in this cliff, and the thing is, if you know how to read them properly, you can kind of create these different environments. Now these are really distinctive. You can see how beautifully rounded all those pebbles are. Look at them, incredible. So they would have started off as just general angular rocks, but what's made them all smooth is water. So this really is evidence that through here, in the past, once flowed a mighty river.
But just along the coast is a different kind of rock formation that shows a very different kind of evidence of contact with water.
What we got in front of us here is it's like just a wall of sand, just layer upon layer of sand dunes piled on top of each other. But in amongst it is these little bands here. There's another one, and they get a little bit thicker, and they look different to the sand above. In fact, if you look in here, how crumbly this is. Because what we've got here is a deposit that's been laid down by really fine sediment settling out of standing water. Essentially, this is a temporary lake among the sand.
You only get rocks with this incredibly fine-grained structure if they were formed when water becomes really still, as it is in lakes and ponds.
So that means that whenever we see a kind of thin band of really fine sediment, we know that it must have fallen out from still water. Using these geological tricks, we've built up this detailed and compelling picture of the history of water on Earth.
Using this knowledge, we can look at the rocks on Mars and reconstruct the planet's watery past. In early 2018, Sanjeev Gupta from Curiosity's imaging team gave the latest update on the search for water.
So where on Mars are we, and what are we looking at here?
So we are sitting in Gale Crater. This is this crater that's about 150 kilometers in diameter that sits at the Martian equator. What we've got here is this incredible mountain. This is Mount Sharp. It's 5 kilometers high, and it's made up of beautifully layered, stratified sedimentary rocks.
You can see that on this image here. You can see those layers working their way up the mountain.
That's right. These are sedimentary layers, and what these are recording is basically progressive build-up of sediment on the Martian surface.
Okay, so something's depositing regular layers of sediment. Okay, well, let's have a look. We can have the next image. There we go.
It's coming up. Yeah, it's a big image. It's a big image.
Okay.
The rock is actually a mudstone. It's a very, very fine-grained rock. We've got hundreds of thousands, if not millions of years of sedimentation in a long-lived lake.
But even after water disappeared from the surface of Mars, it seems it didn't vanish altogether. It just went underground.
Okay, well, let's have a look at one of the more recent images. Oh, there we go. And here we are.
This ridge is probably 3 or 4 meters high here in this face, and just gorgeous detail in terms of the geology. We've been able to use the rover's instruments to actually look at the chemistry of the crack fills, and actually they show evidence for calcium sulfate. So this is actually gypsum that's filling these cracks. And this tells us an interesting story about Mars. After these rocks were lithified, they were turned to stone,
right.
They were buried, and then there was groundwater flow through these rocks, and that groundwater was full of calcium ions and sulfate ions and deposited within those crack fills. The interesting thing about this is that the chemistry, the chemical changes are important to habitability, and that's really crucial. That's why there's so much interest in this.
We now know that Mars once had rivers and lakes, and this surface water persisted for millions of years. What's more, there could still be liquid water deep under the surface today. As we've studied Mars, an extraordinary story has emerged. Mars used to be habitable like the Earth. But over time, Mars lost its atmosphere, stripped away by the solar wind. And with no atmosphere, Mars also lost its water to space, gradually becoming the dry, dusty place we know today. Comparing Earth and Mars reveals that two planets can start off with similar conditions, but end up following very different paths of development. Neither was this an isolated case. When the Sky at Night began broadcasting in 1957, Venus, our closest neighbour, was a planet of mystery. Still thought to be potentially habitable. As Patrick Moore remembered in 1982.
Venus, so like the Earth in size and mass, is a curious world. All we can see from above is the top of a cloud layer. According to two very famous American astronomers, Whipple and Menzel, it was liable to be covered almost or completely with ocean, with only a few islands poking out here and there. Life on Earth began in our oceans, a long, long time ago. And Venus, therefore, might have been a world where life was just beginning and might evolve.
Such speculation was possible because Venus was completely covered in cloud. Anything could be hidden underneath. But when the first successful lander, Russia's Venera 7, reached its surface in 1970, all hopes of habitability were dashed. It revealed an extreme and harsh world. The pressure at the surface was greater than being at the bottom of the ocean. Temperatures were 462 degrees Celsius, and the atmosphere was almost entirely carbon dioxide. The conditions were so brutal that Venera 7 lasted less than an hour before falling silent. Conditions on Venus were obviously hellish, and that provoked a lot of questions.
Just why, do you imagine, Venus, which is so like the Earth in size and mass, has developed an atmosphere which is so utterly unlike ours?
It's closer to the sun, it receives more heat from the sun, the surface gets hotter therefore, and the gases rise from the surface, building up the atmosphere, and as the atmosphere builds up in opacity, so the surface temperature will rise too.
It's a kind of runaway effect.
This is the runaway greenhouse effect. In the same way as heat is getting trapped in your greenhouse at home when you're growing your vegetables, the same heat is getting trapped up here on the Venus atmosphere, building up the surface temperature.
You know, Gary, I remember way back in 1957, 1958, on one of these Sky at Night programs, I remember saying that on the basis of the information we had then, Venus appeared a rather more promising site for a colony than Mars. And how wrong I was, how wrong we all were.
Since the Russian Venera triumph, we've sent a total of 21 successful missions to Venus. They have shown us a planet covered in volcanoes and sulfuric acid clouds. The latest probe to conclude its mission, Venus Express, revealed just how dynamic the planet is, as I discovered in 2015. One of the first things these images revealed was what a constantly changing world Venus is, that is dramatically illustrated by what happens in the polar regions.
The poles of Venus have these enormous vortex features, and it really changes shape quite dramatically from day to day.
It's also changing from year to year.
After 8 years of observations, we've seen, for example, that the mean wind speed at the cloud tops of Venus has increased by 100 kilometers an hour over the course of the mission.
But Venus Express also suggested that, just like Mars, in the past, Venus might have been very different. I met Andrew Coates, who's been studying the way the solar wind interacts with the atmosphere of Venus.
Venus lacks a magnetic field, although unlike the Earth, which is protected to some extent by a magnetic field, Venus doesn't have such a thing. And so the solar wind, which is a 1,000,000-ton-per-second stream of material coming out of the sun all the time, can interact with the atmosphere of Venus and actually pull it away.
So Venus is losing atmosphere?
300 kilograms of the atmosphere per day is actually escaping. Taken over billions of years, this means an awful lot of material has been lost.
So what has surprised you in terms of the results you've got from Aspera 4?
Looking at the composition of the material which is actually escaping from Venus, it actually turns out to be water. The composition is very much like, so you've got twice the amount of hydrogen compared to the amount of oxygen going off. So that's H2O, you know.
Yes.
And so water, yeah. And that was a big surprise because, of course, the atmosphere of Venus is basically carbon dioxide, but it shows that water is still being lost from the Venus atmosphere, and so this dehydration is a process which is still going on and has been going on for billions of years.
If Venus has been losing water for billions of years, it might have once been a wet planet. But then it got hotter and hotter, thanks to greenhouse gases. Water turned to steam, and the solar wind stripped the water vapor away into space. Seen in the light of what happened to its neighbours, Earth is the one that is unusual. Whilst Mars and Venus have both undergone dramatic changes, Earth alone has remained stable and habitable for billions of years. Even closer to the Sun, we find Mercury, a planet with massive temperature extremes and virtually no atmosphere. Today, these four worlds are all very different, but they all belong to the same category: the rocky planets. As we move further out into the solar system, we come to an entirely different class of planet: the gas giants of Jupiter and Saturn. These spectacular planets have led to some amazing discoveries. Perhaps the most surprising is how they've changed our understanding of how the rest of the solar system developed, including Earth. As one of the brightest objects in the sky, Jupiter, named after the king of the Roman gods, has enthralled humans since ancient times. It was one of the first objects to be observed through a telescope. So large that its moons and the striped features were easily visible from Earth.
Jupiter's making quite a brave show, and you can see it in the southern part of the sky late at night. It looks like a very brilliant star, and in fact it's so bright that you can't really mistake it. If you've got a telescope, you'll be able to see its belts and its moons. This is a picture of Jupiter which also shows that extraordinary feature, the Great Red Spot.
Our exploration of Jupiter began in earnest in 1979 with the two Voyager spacecraft.
571, item 1, NA, item 2, command mod off, 0235.
Good evening. As I think most people will know, the American probe Voyager 1 has flown past the giant planet Jupiter and sent back incredible results. And this, in fact, is a film made up of the various stills taken as the probe went in. And you can actually see Jupiter spinning around. And don't forget that Jupiter has the shortest day in the entire solar system, less than 10 hours long. There it is, there's the Great Red Spot below the center.
What we see as Jupiter's colored bands are in fact the tops of giant weather systems. A layer of swirling cloud tops that go down 3,000 kilometers. The Voyagers confirmed theories that the Great Red Spot, observed for hundreds of years, was a gigantic storm, twice the size of Earth. But how had it persisted for so long? Helen Chursky met Professor Peter Reed to find out how temperature differences between the different bands of weather can create very stable features in the atmosphere.
What we tend to see is that the main temperature differences that we can measure in the atmosphere are actually between the bright bands and the dark bands, so that you will typically have a bright band which is relatively warm, and then to the north and to the south of that, there'll be a dark band that is relatively cold.
With this experiment, we're trying to create a simulation of what happens within one of Jupiter's bands. The water is heated, but the edges and the centre of the vessel are cooled. This represents a warm band on Jupiter surrounded by colder air, and then the whole experiment is rotated. After a few minutes, some vortices are created that are so stable they barely appear to move.
So what you can see now is a whole chain of these eddies that are all circulating in the same sense.
So if this was a band on Jupiter, at the bottom of the band the winds are going this way around, and then you've got these eddies spinning like this, but at the top the winds are going the other way.
That's right. So this is just like the bright bands on Jupiter. So the south, the jets will be going in one direction, and to the north they'll be going in the opposite direction with these vortices rolling in between them.
These rotating storms are trapped within the bands that have been created by Jupiter's fast rotation.
Since the Voyager probes, we've sent another 5 probes to Jupiter and discovered it has northern lights up to 1,000 times brighter than on Earth, an intense magnetic field, and deadly radiation zones. But perhaps the most surprising discovery we've made about Jupiter is that it plays a key role in keeping Earth habitable. In 1992, scientists spotted a comet they called Schumacher-Levy 9, which had broken up into pieces and was on a collision course with Jupiter. Telescopes, including the Hubble Space Telescope, were trained on Jupiter to record the impact. The Sky at Night looked back at the event 2 decades on.
In July 1994, 21 fragments of what was the comet Schumacher-Levy 9 crashed into the atmosphere of Jupiter, and Hubble was on hand to witness the event. The impacts happened just over the limb on the planet's far side, though the plumes were detected from Earth. But the true enormity of what had happened became apparent slightly afterwards, as Jupiter rotated, bringing the impact sites into Hubble's view.
The wonderful thing about this event was that no one had any real idea what to expect. We hoped we might see the impacts with Hubble, but that was about it. And I remember going outside with my own small telescope and being able to see these bruises on Jupiter's surface, and then to see the Hubble images afterwards made for a really thrilling event.
The resulting impacts were more profound than anyone had predicted. Using different wavelengths of light, Hubble captured striking images of the impact scars, revealing some to be twice the size of Earth. At the time, we thought it was a once-in-a-lifetime event. But we now know differently, thanks to the work of amateur astronomers who monitored Jupiter constantly. They've spotted several unusual spots over the years.
In 2009, quite unexpectedly, an amateur, Anthony Wesley, discovered such a spot on the planet. This was an image he took 2 nights earlier, and then he saw this remarkably black spot appearing and realized that this might well be an impact. So other amateurs immediately started taking images to confirm, and professional scientists took this image in a far infrared wavelength. The Hubble Space Telescope took this image a few days later. And so the professional astronomers managed to follow this event over several months. While we amateurs were also tracking it over several months.
So the amateurs are the watchkeepers. They keep an eye on Jupiter and then alert the professionals when something really exciting happens.
Yes, indeed. And more recently, amateurs have been noticing impacts while they happen. They're much smaller impacts. They don't leave visible scars, but they're more frequent. And so now 3 times since 2009, amateurs have actually seen fireballs in the atmosphere of Jupiter. Which previously, if anyone had seen them, they didn't notice them or didn't believe they were seeing them. But now we have real webcam videos, and it's clear that amateurs are actually detecting flashes as they occur.
Jupiter's enormous gravity acts like a giant magnet, sweeping up comets and meteors that might otherwise collide with Earth. Without Jupiter, Earth might have faced many more meteorite impacts, like the one that wiped out the dinosaurs. That would have made it much more difficult for complex life to develop. Jupiter may be the biggest planet in the solar system, but it isn't the most spectacular. Saturn, with its incredible ring system, is perhaps one of the solar system's greatest planetary wonders. It's also the planet that sits furthest away from the Sun that can be seen from Earth with just the naked eye. And its iconic rings have puzzled astronomers for centuries. What are they made of? How were they formed? And how many rings are there?
Saturn. This is the planet with the rings. A magnificent sight. There's nothing else like it in the sky so far as we know.
Saturn sits 1.4 billion kilometres from the Sun. And so far, we've only sent 4 missions there. The first was Pioneer 11 in 1979.
This is Saturn, photographed from close range. Since our last Sky at Night program, the space probe Pioneer 11 has flown past the ringed planet and has sent back pictures which are surprisingly good, as well as a great deal of fascinating general information.
But we had to wait 25 years for the definitive mission to Saturn.
And liftoff of the Cassini spacecraft on a billion-mile trek to Saturn.
Cassini, which arrived in orbit in 2004, spent 13 years orbiting the planet. It revealed enormous hurricanes, 8,000 kilometers across. And we finally saw Saturn's rings in all their complex glory. They're made almost entirely of water ice. Some particles the size of grains of sand, and others as big as mountains. They're 280,000 kilometers across, but astonishingly, only 10 meters deep. And they show incredible complexity. There are 7 groups of rings, and each one has its own unique, intricate structure. What's more, Cassini discovered remarkable and unexpected interactions between Saturn's rings and its moons. Gravity from the moons could clearly be seen to be dragging the rings out of shape. But the relationship between the moons and the rings went further than that.
This is the moon Enceladus. So this is active. We think there's liquid water, possibly even a global ocean of liquid water underneath. And this material is coming out at pressure and going out to several hundred kilometers, and then just sort of wandering around. If you just look up really closely, you can actually see the plumes of material coming out of the South Polar. And that has created the entire E-ring. So it shows this connection between rings and moons.
Yeah, and it seems to be quite a strong one. It seems that at least some of Saturn's rings are formed from material ejected from Saturn's moons. But there's a twist to this discovery. So, sort of moons forming rings, and then sometimes rings forming moons?
Yes.
I find that surprising.
I did too when it was first proposed, but we know that material kind of naturally kind of accrete in the rings. Supposing you get a large enough mass, then it could start evolving as it interacts with the ring material around it, and maybe even escape from the rings, and then move outwards, and then maybe catch up with another one that had already escaped and get larger. And they originally proposed it for small moons, and they think not. Maybe even the larger moons of Saturn, and indeed other giant planets, could have formed in this way.
This process helps us understand the early days of the solar system. Now, you have this sort of, what I like to call an accretion disk, with a large mass in the centre.
It's very similar to what we think the early solar system was like, that there was a disk of material out of which the planets formed in that case. And this is a disk that we can study in detail now, and we can see how things evolve now, and then try and extrapolate to what went on in the early solar system.
So by studying the rings of Saturn, we can actually look back to the formation of our whole solar system. When we leave the gas giants behind, everything changes again. We meet a whole new class of planet, the ice giants of Uranus and Neptune. Even as recently as 1975, we had no clear photos of Uranus and Neptune.
Well, I'm afraid you're not going to see very much on Uranus with any telescope. I can show you a picture of it, and here is one taken with a major telescope. And you can see there some of Uranus's satellites as well. But not even a giant telescope is going to show you very much on the disk. And here is Neptune. But as I've said, I'm afraid no telescope is going to show you very much on it. We've got, I think, to wait for the era of space probes.
Only one probe has ever visited these outer planets. Voyager 2, and only by flying past, not going into orbit. When Voyager arrived at Uranus in 1986, what it found was far from what we had imagined.
Voyager flew past Uranus and saw a greenish disk with very little cloud activity taking place over the disk itself.
It was a really boring planet, let's be honest about this.
Well, lots of scientists looked at it and were quite disappointed.
But observations over the next quarter century showed us that first impressions aren't always accurate.
We've got a large data set of Hubble Space Telescope and ground-based observations of Uranus, which show that we simply flew past at a rather boring time. And in fact, it's become a lot more active now with white spots, incredible collars around the North Pole and the South Pole.
Uranus also has its own ring system, and a bizarre feature that makes it unique amongst the planets. It's tilted so far over that it's completely on its side, giving it extreme seasons. In contrast to Uranus, Voyager found Neptune's surface to be turbulent and active, with the strongest winds in the solar system.
Neptune has its own source of internal heat. It emits out more energy than it's receiving from the sun. And that emission of heat is driving a really complicated weather pattern. We see incredible storms, such as the Great Dark Spot that was present in Neptune when Voyager 2 flew past in 1989.
Uranus and Neptune have different characteristics, but also they share significant similarities. They both have a blue-green hue, and they're both made of similar materials, including methane, ammonia, and water. Looking back at all the planets in the solar system, it's striking to consider how they fall into three distinct groups. The rocky planets, closest to the sun, then the gas giants, and finally, the ice giants. The question is, what could explain this pattern? In 2014, physicist Chamkor Garg took on the challenge. It meant going back to the formation of the solar system, when there was a huge cloud of gas and dust, and a newly formed star in the middle.
Imagine this bench is our disk of stellar dust, all the bits and pieces that are going to go into making our brand new solar system. Now in the center, the sun pushes the temperature up by over 1700 degrees Celsius. But as we move away, the temperature drops. And down towards the edge of this disk, an incredible 9 billion miles away, the temperature has dropped to a chilly minus 250 degrees Celsius.
This temperature gradient from inferno to freezer is critical to the way each planet is formed.
Here, close to the center of our primordial solar system, the temperature's upwards of 1,000 degrees Celsius. In this searing heat, only certain rocks and metals can remain solid, and that's why Mercury, Venus, Earth, and Mars are made up mostly of rocks and silicates. As we move further out into the solar system beyond Mars, we reach the snow line, an imaginary line where the temperatures drop to 0 degrees and water ice can form. Now, what's really interesting about this is that ice sticks together much more easily than rocks do.
And this explains why gas giants Jupiter and Saturn are a bit like these balloons, filled with hydrogen and helium. The ice helped the cores of these giant planets to form very early and suck up vast amounts of gas from the protoplanetary disk.
It's only when we get further out, much further out, double the distance from Earth to Saturn, that we start to see the ingredients of the ice giants appear. By the time we're at the orbit of Uranus, The temperature is so low that it's not just water turning into ice. Complex gases like methane and ammonia are forming ice as well. Suddenly, now that these volatile gases are locked into solid form, they can start to coalesce, and they seed what will become Uranus and Neptune.
Although today, the planets are considered to end at Neptune, that hasn't always been the case. When I was growing up, Pluto was very definitely considered to be the solar system's 9th planet, but not anymore. In 2006, it was demoted and given dwarf planet status. But this raised a rather interesting question. Just what is a planet? Pluto was demoted, partly because it's small, but also because it's not something known as gravitationally dominant. Pluto sits in a region of the solar system called the Kuiper Belt, a vast realm of icy bodies of many different sizes. Its weak gravity means it has not cleared the area around it of other objects. Nevertheless, the debate over Pluto's status hasn't gone away. When NASA's New Horizons mission arrived at Pluto in 2015, it turned out to be one of the most exciting and surprising space missions of all time.
Stand by for telemetry.
This is good.
For Alice Bowman, it had been a 10-year wait.
Okay, copy that. We're in lock with telemetry with the spacecraft.
I told you it would be fine. I wasn't worried. These people weren't worried.
I was worried. I was worried. This is such a culmination of so much work.
They'd travelled 3 billion miles and hit a target that was only 60 by 90 miles. That's the equivalent of throwing something across the Atlantic Ocean and it landing in my hand. Pluto astonished everyone. It had huge nitrogen glaciers and mountains made out of water ice, completely impossible here on Earth. Carly Howard explained why the team was so excited.
So you have to remember that the surface isn't rock, this is water ice mountains.
Which sounds crazy.
That's crazy, right? Like water ice in the Earth just wouldn't be strong enough to sustain that sort of structure. But what you're looking at on Pluto are temperatures, surface temperatures that are so cold that water ice almost has a sort of rock-like quality of it. It's just absolutely solid. And so it's able to support these massive structures.
I don't remember anyone predicting mountains. Do we understand how these things could have grown?
I have no idea how those mountains could be formed. Pluto has quite low gravity, it's a small body. I mean, we don't get like winds and water like you do on the Earth, so how you get uplift, how does that even happen? I don't know.
The discoveries reignited the debate about Pluto's status. In 2017, a team of scientists submitted a proposal to reclassify Pluto as a planet. For now, though, Pluto is just one of a vast number of bodies going round the Sun in distant orbits, all part of the Kuiper Belt. And it's in this distant realm that our solar system has given us one last planetary surprise. In 2016 came a dramatic announcement. A claim that scientists had discovered a new 9th planet. If true, it would transform our ideas about the solar system. The strangeness of this proposed Planet 9 began with its extraordinary orbit about the Sun, as I tried to demonstrate. On this scale, every centimetre is about 35 million kilometres. The Earth is 150 million kilometres from the Sun. Pluto is 40 times further away, and the outer edge of the Kuiper Belt is still further. But if it exists, the orbit of Planet 9 is far beyond that. At the point of closest approach in its orbit, it sits 200 times further than the Earth. That's a whopping 30 billion kilometers away from the Sun. But unlike the other planets, the proposed orbit of Planet 9 is not circular. Its highly eccentric path takes it much, much deeper into space. At its furthest possible point, it's aphelion. In reality, it would be 180 billion kilometers from the Sun.
This discovery was enormous news, but there was one crucial stumbling block. No one had actually seen Planet 9. Its existence had only been predicted by computer models that had been built by Caltech astronomers Mike Brown and Konstantin Batygin.
In 2003, Mike discovered the first of 6 objects with bizarre orbits in the Kuiper Belt. All of the orbits pointed off in the same direction. They were all tilted downwards and off to the side.
And the combination of those two is what really shows you that there's something strange going on. So it's about 0.01% chance that this is all just randomly aligned.
So is that what got your attention and got you working on the problem?
That was the big clue that something is going on in the outer solar system.
This was an extraordinary finding. The tight clustering of the 6 orbits might have been caused by the gravitational influence of something massive in the outer solar system. For Mike Brown, the question now became what was out there and how could he find it? Working down the corridor from Mike is theoretical astronomer Konstantin Batygin.
Hey, how's it going?
Yeah, nice to see you. And so Mike challenged him to build a computer model of the solar system that would replicate the strange orbits of the 6 Kuiper Belt objects.
After many calculations, Batygin came up with a model that worked.
But there was another unexpected effect. The model also predicted a second set of Kuiper Belt objects with even stranger orbits. Trouble was, they didn't seem to exist.
The biggest twist to the whole story came when our numerical models consistently would generate orbits that looked more or less like this.
So sort of coming in and out of the blackboard here.
That's right. They are on their sides. They're perpendicular to the plane of the solar system. Right? And this is just so weird. You know, the fact that the simulation is producing these orbits that should be perpendicular, they should be readily observable, and the fact that we don't know of them is big trouble.
So it's not just that they might be there, they have to be there.
We initially thought of this as counter evidence to the existence of the planet. Fine, it explains alignment, but it also predicts stuff that's clearly not there.
This was the key moment where we looked at it and said, this makes no sense. But then I started looking more carefully at the other objects in the data set that I had not been paying much attention to in the last couple of years. There are 5 of these objects that are on perpendicular orbits that I remember when one of them was discovered a few years ago and thinking, that's just weird. Nobody had any explanation for them. And I said, Konstantin, I'm going to go plot these right now, and we're going to see where they are. And if they're sitting right at these 2 spots right here, my head's going to explode. And we plotted them. One of them is right here. 4 of them are exactly right here where we predicted. And we just both sat there and stared at that. And I think my jaw hit the floor. It really was an honest, blind prediction of something we didn't know was there. And that when I look at those objects on those wings, and then I see those aligned objects too, I think I really am pretty convinced it's really out there.
So far, Planet 9 is just a theory. It has yet to be discovered. The planets of our solar system are amazingly varied, but they are just one case study, orbiting our star, the Sun. But the Sun is amongst billions that lie in our galaxy. For many years, we've thought that there must be other planets out there in the galaxy beyond our solar system, the so-called exoplanets. and some might even be habitable like our Earth. But we've had no way of finding them. Planets with no light of their own were rendered invisible in the glare from their parent star, as Patrick explained in 1975.
Now that's the view from close range. Now we are going to pull the cameras back and you will see what happens. As the sun shrinks from a large disk into a smaller one, so the little Earth gets closer and closer to it and finally disappears. Now just imagine what would happen if we could go so far away from the sun that it looked merely like a point of light. What would be the chances of our being able to see a world such as the Earth going round it? Frankly, none.
But then, scientists came up with a new way to search for exoplanets that meant they didn't have to see the planet to know it was there. It involved looking for tiny movements in the stars, wobbles, caused by the planets pulling them off-center due to gravity. In 1995, 2 young scientists from Geneva, studying a star called 51 Pegasi, made a breakthrough. Didier Queloz, who made the discovery, told me what happened.
I was a PhD student at the time, so the first time I saw something a bit strange going on the series of measurements I made on 51 Peg. I never thought it would be a planet, because it was just impossible. I thought it was a bug into the instrument. Something was wrong with the instrument, with the machinery, and it took me a long time to figure out exactly what it was.
This was no data error. Didier had found the first exoplanet orbiting a stable main sequence star, 50 light-years away from Earth. Did you hope that the planet you discovered was going to be Earth-like?
Well, it was impossible, because the instrument we were using, the best it could do is detecting something like Jupiter. And it was designed to do that. That was already a tremendous achievement at that time.
The technology then could only detect the most massive planets, because they exerted the biggest gravitational pull on their host star, resulting in a bigger wobble. 51 Pegasi b was spectacularly weird. It was the size of Jupiter, yet it took just 4 days to orbit its star. And its surface temperature exceeded 1,000 degrees Celsius. It was a type of planet that has come to be known as a hot Jupiter, and it rewrote our ideas of what a planet could be like. But there was no chance it might be habitable. Now the hunt was on for more exoplanets.
Engine start, 1-0, and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Chamber pressures are building. Outlet solid.
When NASA's Kepler telescope was launched in 2009, it unleashed a planet-hunting gold rush. Designed to stare at a patch of sky continuously, Kepler measures any subtle dimming in a star's brightness, a signal that a planet could have passed in front of a star. Using this technique, Kepler has found over 2,600 exoplanets in many different flavors. Hot Jupiters, mini Neptunes, and even so-called super-Earths, just a few times bigger than our own planet. To explore just how strange some of these planets are, the Sky at Night decided to compare the planets that science fiction had imagined in movies with the real planets that had been discovered.
So how realistic are some of these exoplanets that we see in the movies? The planet Tatooine from Star Wars, for example, you've got this wonderful, evocative desert landscape, and Luke Skywalker stands there contemplating his destiny, bathed in the afternoon light from not one, but 2 suns. Could something like that happen? If so, have we found anything like that?
Yes, absolutely. We found more than one, actually. The first one we found was Kepler 16b. We found it in 2011. And it's the first circumbinary planet. So that means it's a binary star, 2 stars that orbit each other, and a planet on the outside that orbits both of them. So the planet has
So the
two
stars
suns.
are orbiting each other in a
Yeah.
little sort of merry dance, and the planet's going around all... Oh, wow.
Exactly,
Okay.
yeah. So here's a video of that system. And you can see there's the binary star in the centre. One is a little bit more massive than the other, and it's slightly whiter.
Yeah.
The other one's a little red.
Almost exactly like in Star Wars. I have to
It
say, it's
is
got a red one.
almost exactly like in Star Wars.
One of the things about Planet Miller in Interstellar is that it's orbiting a black hole, and you get into all kinds of exotic physics, time dilation, all this sort of stuff. But the fact that it's orbiting a black hole is a really interesting idea. Is that at all feasible?
Yeah, there's no reason why you can't have a planet orbiting a black hole. And in fact, there is some evidence to suggest that we've even seen a super Jupiter being eaten by a black hole.
We've even found a planet that might be made of diamonds.
There are lots of things that we've found that are stranger than things we can imagine. And that's the beauty of the exoplanet world at the moment. We're discovering things that we didn't even know were possible, and new physics is being discovered all of the time.
Although we were constantly being surprised by new exoplanets, we still hadn't found anything that seemed potentially habitable. What we needed was a rocky planet in the Goldilocks zone. Not too hot, not too cold, but just right, hopefully with liquid water on its surface, and therefore the potential to support life as we know it. In 2016 came a breakthrough.
Now, scientists are hailing a major discovery, a new planet which they've called Proxima b.
The planet was found orbiting Proxima Centauri, our closest neighbouring star. At just over 4 light years away, it's close enough to imagine that we might one day be able to send a spacecraft there. And so a French team have tried to work out the planet's characteristics by using comparisons with the planets in our own solar system.
If it has a large metallic core and a rocky mantle like Mercury does, then it's probably a little bit smaller than the Earth. But there are other, more exotic possibilities.
It could be much bigger than the Earth, 1.4 times the size, in which case it would have to have a rocky core surrounded by a mantle of ice. And excitingly, the models suggest that the entire planet would then be covered in a vast ocean, 200 kilometers deep.
Proxima b was tantalizing enough, but then, in 2017, came the most exciting discovery yet. A whole system of Earth-like, potentially habitable planets, known as TRAPPIST-1. In just 60 years, we've gone from one solar system of 9 planets to a galaxy teeming with them. So, what's next for planetary exploration? Well, if there's one lesson that we've learned through over 60 years of the sky at night, it's this. Every mission we send out to another world throws up incredible discoveries and provokes many new questions. Really, we've only just begun.